All right. Hello, everybody. We're just waiting about 1 or 2 extra minutes for Laurent to join. He is the engineer that will be running today's session. In the meantime, what I'm going to do, we want to make sure to make these webinars as collaborative as possible. So what I'm going to do, I'm going to start a poll for you guys. We're curious to learn a bit more information about your guys' wind loads, how you guys are designing them, what the most important or the most annoying part of your wind loads are. So I'm going to go ahead and launch this poll, and feel free to go ahead and answer. If you have any additional thoughts, go ahead and put your thoughts here in the chat. And then we'll just wait. It looks like we just got a small group so far today. I know a lot of people signed up for this one, so we'll give everybody a minute or so to come in and sign up. It looks like we're so far transferring wind load to my buildings is winning, but definitely feel free to include in the chat here. And like I mentioned, if you're just joining us, we're just waiting an extra minute or so for our engineer to join. It looks like we might be having some technical difficulties here. It looks like there's a couple meetings going on. Give me 1 second. Very sorry, everybody.
Is that you?
All right, here we go. It looks like Laurent was able to join here. Sorry about that. And then yeah, if you're just joining here, we've got this poll right here on the Zoom. So curious to learn a bit more about the wind loads that you guys are designing and what the most annoying part of that is. Anybody who said other, go ahead and pop your additional information in the chat here. All right, Laurent, and I just gave you screen sharing permissions. So whenever you're ready, you should be ready to go. Awesome.
Oops.
Perfect.
Okay. Hello. Good morning, afternoon, everyone. Y'all got me? Can you see me? Perfect. Sorry, we ran into a bit of technical issues here, but we're good to go now. Okay. I guess Connor, if you want to start us off.
I'll kick it off. Yeah. And apologies again, everybody. As much as we love technology, it always inevitable. It gives us issues at some point. You'd think we'd know how to use Zoom after being in, I guess we're post-COVID now, but it's 2023 already. But today we're going to be talking about calculating wind loads. As you guys saw from the poll, asking you guys a bit more information about the most painful part of calculating wind loads for you. Like I mentioned, it looks like what we have, the most annoying with 5 out of the 10 respondents there was transferring wind loads to my buildings. That's the most annoying thing. And then we had finding the appropriate factors is the next annoying, and then finding my local wind speed after that. And if you did say other, feel free to pop in the chat. Also in the chat, feel free to, introduce yourself, name, title, where you're joining us from. Always love to build this ClearCalcs community. All right, and then you guys know we got to do it. The aboutclearcalcs.com. This is a ClearCalcs sponsored webinar. So ClearCalcs is a cloud-based structural engineering platform, structural calculations platform, looking to combine powerful FEA analysis with easy-to-use tools, such as tools for wood, engineered lumber, steel, concrete, cold-form steel, looking to be more accurate, doing that through our transparency. If you guys have used ClearCalcs, hopefully you've noticed, we call it internally the debug mode. I've referred to it as the help accordion to some of you guys. Get additional descriptions, code references, standards references in there to make sure we're all on the same page. We want to eliminate wasted time, using load linking, member selector, quick swap material, any other features as well. And then, like I mentioned, cloud-based platform, so we are available everywhere. Meeting the presenters, you guys hopefully know us by now if you've been to one or two of these webinars. But I'm Connor. I'm our Director of Customer Success. Whether it be training sessions before or after you sign up, sending you the right help content, reach out to me. Always happy to help. And then we have Laurent here, who's a professional engineer, North American engineering content lead. He's leading all the calculator work in the US and Canada. So all these new calculators that you guys are seeing come out in the past weeks or the past years, if you've been with us for a while, Laurent is the main guy to thank for that. And of course, the rest of his team. Lastly here, if you guys are unfamiliar with Zoom, it looks like most of you guys are already posting in the chat. If you have questions or comments, anything like that throughout today's webinar, definitely utilize that chat button. The more collaboration we get going in these webinars, the better they end up being. So feel free to send questions, and then we will address the questions in the second half of the webinar during the 15 to 30 minute Q&A session. And then we also might ask you to unmute yourself if you're interested in asking the question live. And then from here, I'll pass it on to Laurent.
All right, and apologies, I forgot to put a picture in this slide. I just realized, so it's a bit of a bland one, but you'll forgive me for that, I hope. And second apology, I'm a little under the weather today, so if you hear me mumbling or coughing, apologize in advance. That's it though. So today you all signed up for a wind webinar, so I hope you're ready to get windy. I think that made sense. Anyways, what we'll be talking about today, we're going to go over kind of the basics of wind loads. What are the things that we want to consider when we're talking about wind loads? Then we'll briefly touch on how we apply these wind loads to buildings with a specific focus on residential buildings. You're not going to learn how to design wind for a skyscraper today. Let us know if that's what you're doing, though. That'd be interesting for us to find out about. And then we'll go through two worked examples in ClearCalcs at the end using our wind calculator. So, basics of wind loads. If you've been in a webinar with us before, you might have seen the Three Little Piggies story come before. We like them because they make for great analogies. But basically, wind, what it is movement of air, right? And it generates air pressure on buildings, and that turns into loads. And there's kind of two main types of loads that we'd consider here: lateral loads and then roof uplift. And I like this picture because it indicates it exactly. The two modes, right? Uplift is your roof flying off, and then lateral is your whole building either racking or overturning or shearing sideways from the wind loads. And then the biggest thing, obviously, with wind load is wind speed. You just have to go outside during a storm to know that the faster the wind, the stronger it's going to feel, and therefore buildings feel the same thing. But there are a few other things that we need to consider when we're talking about wind loads, so we're going to be talking about those today. So we are talking about wind in the United States. ASCE 7 is the law of the land here almost everywhere. If you're working with another wind code in your jurisdiction, we'd love to hear about it. But as far as I know, mostly everywhere is ASCE 7. That's where you'll find your formulas, your design values for your wind speed, things like that. These are all in this reference. So definitely a must-have when you're thinking about designing for wind. One thing to keep in mind, obviously, is your local jurisdiction or your state building code might make some amendments to it. Most common one is, especially in bigger counties, the county might set a specific design wind speed that kind of overrides the ASCE 7 maps. So definitely double check that when you're working with wind loads. Right now, ASCE 716 is what's used in most states. That's what's referenced by the International Building Code 2018 and 2021. International Building Code 2024 will be switching to the 2022 version of ASCE, so the latest version. And recently learned as well, the Florida Building Code that's coming out at the end of this year will also be using the 7 2022. And there are still a few states that are using the 710 version, which is a bit older. I believe there's Indiana, Iowa, and a few other states. So obviously, if you're working in that state, you're probably aware of this, but good to keep an eye out for these things. So we talked about wind speed being the most important part of designing with wind. So big thing here, if you open ASCE 7, you'll find this map, right, which shows these contour lines for different wind speeds. Big thing here is you want to use the right wind speed. The wind pressure, so the actual loads that get applied to your building, they scale with the square of the speed. So just as an example, I was looking, if you going from 100 mile per hour wind to 140 mile per hour wind, you double your wind load. So it's a 40% increase in speed, but 100% increase in load. So it's pretty significant. And especially if you're near the coast, say the Gulf Coast, the East Coast, even within a few miles, you might get a 10, 20, 30% difference in wind speed. So again, this is one where you might want to check with your local jurisdiction to see what wind speed, if any, they specify. Otherwise, probably better to err on the side of caution because, as I said, the gradient on wind speed here is so high. You really want to make sure you're using the right wind speed. It's got a huge impact on your design loads. Next, we've got exposure categories. And so this might be something that you feel if you're walking, say, you're going hiking and you're in a clear area where there's no trees and it's windy, you feel it, and then you get in the forest and then all of a sudden it's calmed down a lot, there's a lot less wind. What that is basically this exposure category. So there's 3 categories in ASCE 7. It starts at B, ends at D. There used to be a exposure A, but that is no longer in the standard. But exposure B is basically anything urban, suburban, where you've got trees, you've got buildings that kind of shield the wind. Exposure C is anything on land that's a field. Maybe you've got a couple trees here and there, but overall the wind is unimpeded. Again, this kind of like the transition, right, where you're walking in the forest. Exposure B, you're walking in the forest, not feeling any wind. Exposure C, you're out of the forest. You can still see it, but you're feeling a lot more wind. And then exposure D is generally anything where you're near a big body of water. So the Great Lakes, the oceans, something like that is where you'd be looking at exposure D. And in general, for residential design, you're going to be looking at the worst case exposure. So you might have, say, you might be building at the edge of a new development where on one side you've got exposure B and then on the other side you've got exposure C. You would, in general, just pick exposure C for everything. And that's the conservative option. Now, if for some reason you were finding that these loads are inappropriate or are far too high, you might be able to change these exposure categories or adapt these exposure categories. And the standard does have some instructions on this. But we're not going to jump into that. We're going to just stay here saying almost all the time in residential building, you're going to want to look at just the worst case scenario for exposure. Next one is topography. And this is an interesting one. And I'd love to hear if you typically consider topography in your designs. This is one where I got a nice little picture here, a great place in Italy. I'd love to go visit one day, where you see these houses. Obviously, they're on the side of the coast, so there's already high winds. But this topography with the mountains is a prime example here of just because it's on top of a mountain, the wind loads will be significantly higher. So this is something that you need to consider if you're building anywhere near the top of a hill, a ridge, an escarpment, anything like that. You need to consider this. And what's interesting is if you look in the standard, this can actually apply for hills that might be as low as 15 feet. So really small hills might actually have a pretty significant impact on your wind speeds. Sometimes it can actually, or wind loads, I'm sorry. And that can actually easily double your wind loads sometimes. So significant increase in your wind loads. Very easy to miss because, to be honest, the calculations are not that straightforward, but it can have a big impact on the wind loads. So I'd love to hear if this is something that you typically calculate based on your geography or your project. Another one is elevation. So obviously, as you've probably felt if you've been in an airplane or something like that, as you increase your elevation, the air gets thinner, there's less air molecules in the air. And so the air density actually gets lower, and that means lighter wind loads. There's less air molecules hitting your building, basically. And just for fun, I looked. So if you're in Colorado Springs, which is where Connor, my colleague here, lives, and you've probably spoken with him. If you're in Colorado Springs, you'd actually get about a 20% reduction on the wind loads. So compared to, say, if you're doing the same building at sea level. So it's a pretty significant reduction, and 20% reduction might mean you get to go to a slightly smaller sheathing size or something like that. So something to consider. And what's cool is in ClearCalcs, if you enter your project address, we'll actually automatically calculate the ground elevation for you, and we'll calculate that factor for you. Lastly, a very important one is the building enclosure. And what that does is basically we think about what's going to be the difference in pressure inside the building and outside the building. So obviously on the outside, the pressure is the wind pushing against the walls, against the roof, or doing suction against the roof or the walls. And you've got a picture of that on the left here. On the inside is where things get a little bit more tricky. And the standard kind of simplifies this a little bit, and they give us 4 different categories of buildings. So the first one is the enclosed building, and that's pretty straightforward. We're saying there's basically no major openings, and if there are openings, we are completely sure that they'll be closed and unbroken during a storm. So especially if you're near the coast, you might have some protected openings, or they might be missile resistant or something like that. So that's something that you would consider in an enclosed building. Next, we've got partially enclosed, and this represents a vast majority of buildings, especially when we're talking about residential. And this is where the airflow can go into the building. So you can see that the middle picture here, into the building. It fills up the building with air, increases the pressure, but there's not quite enough openings as well that the pressure can get out of the building. So what it does is it basically tries to inflate the building like a big balloon. And at the same time, you've got the wind pushing on here, you've got the suction going on here. So that can create some really high wind loads, especially when we're thinking about components in cladding. And so that's where we're considering here for partially enclosed. So that's the worst case generally for enclosure in terms of the net wind loads that get applied to the wall. But unfortunately, it's also probably the most common one. Next, we've got partially open. And what's interesting is most standards before this version didn't actually include a partially open category. That's new with the 2016 version of ASCE 7. Basically, what it means is anything that's not enclosed, partially enclosed, or open. That's literally their definition. But the idea here is that you've got some air that can go into the building, but there's also enough openings that they can probably get out, so that the internal pressure is not nearly as high as a partially enclosed building. And finally, we've got the open building, so a gazebo like this or something like that, where the airflow is just right through it. And so there's barely any walls or area for the wind to hit. And so the wind loads are obviously much lower. There's no internal pressure at all, actually, in a building like this. So we're talking about wind. Next thing is obviously, how does this actually affect on my building? So there's 2 different ways that we'll look at wind loads on buildings. First one is components and cladding, and then the second one is the main wind force resisting system. And we'll talk about these 2 in separate slides just coming up, but these are the 2 main ones that we want to think about. And then on top of that, I spoke about it earlier, we've got lateral loads and uplift. And then in some cases, we'll also need to consider torsion. So that's when, say, the wind is acting a bit more on one side of the building than the other. But almost all the time, if you're dealing with small residential building, like a single family houses or a low-rise building, you can usually get away without considering torsion. There are exceptions in the code that let you avoid this. Okay. First one that we're going to look at is components and cladding. So what is this? This is literally, you're thinking about your shingles on your roof. You want to make sure they don't fly off. You're thinking about your cladding, your facade, your brick facade. You want to make sure it's not going to be damaged by wind. It's also thinking about stuff like studs in a tall wall. You want to make sure they're not bending too much. It's also thinking about rafters. That's what we're talking about with components and cladding. Basically, anything that's kind of a local small component of your building. And what's important here is that the loads on these are completely governed by turbulence. And what that means is they've literally put models of, say, a typical house in a wind tunnel, and they'll look at, at the corners, because you've got so much difference in the geometry, there's a lot of turbulence here, so that really increases the loads. Whereas, say, in the middle of your roof, where it's a relatively flat surface, not too many obstacles around it, your wind load, there's less turbulence or something like that, and so your wind loads would actually be lower. So for small buildings like houses, ASCE 7 is very convenient. They just give you a nice picture with different zones, and they tell you what coefficients you use, and you just get your wind loads in PSF based on that. Obviously, it gets a little bit more complicated with more complicated buildings, but for residential, that's really all we need to deal with. Big thing again is talking about the building enclosure. If we're thinking about pressure on the inside of a building, this also has an impact with the components in cladding. If you think about your studs in a tall wall, obviously if your building is trying to blow up like a balloon, and you've also got the wind causing suction on the outside, those two things are going to add up, and it makes your stud bend even more. And important thing here is that the components in cladding loads, they get much lower as your tributary area increases. So what does that mean? Basically, we talked about turbulence and how it's very local effects. If we compare about, say, a single shingle, it needs the turbulence only needs to happen over that single shingle for it to fly off. Versus if you're thinking about a entire rafter, you would need a lot more turbulence, a lot kind of worst case scenario over that entire length of that rafter, all happening at the same time to get the worst case. So basically what it means is you kind of average out this turbulence over the entire area of the rafter, and it ends up being a much lower value than, say, if you're only looking at a specific shingle, something like that. And then the other type of wind load that we spoke about was main wind force resisting system loads, or as we tend to call it here at ClearCalcs, the MWFRS loads, not a type of dinosaur. So these loads are typically, they'll be applied over the entire area of the building. So this is where you're thinking about, is my building going to overturn? Is my building going to shear? Or is my foundations going to slide or something like that? So in this case, we don't care about the local turbulence much. We don't care about that single shingle flying off. We care about the entire building standing up in a big storm. And so when you're thinking about, I'm sure you've seen some pictures perhaps of the, skyscrapers in New York or something, where they've got the crazy dampers and stuff like that for vibrations. That's where you'd be thinking about the main wind force loads. And these ones would be a lot more complicated. Basically, you're thinking about the vibration in the building, you're thinking about natural frequencies. Luckily, if we're dealing with low buildings such as residential housings, and if they're rigid enough, which the standard gives a definition, but most houses would meet that definition, things are a lot simpler. We basically just get a factor of 0.85, we apply to our wind loads, and that's it. We've accounted for the vibrations and all that fun stuff in there. Now, when we're talking about ASCE 7, there are two methods to calculate the MWFRS loads. So the first one is the directional procedure, and that one is basically the most universal. You look at your building from different directions that the wind comes in, and this is where as well you could consider different exposure in the different directions. You look at that in the different directions. Very universal, works for almost any kind of building, and you get your wind loads that way. The other method is the envelope procedure, and that one only applies for low-rise buildings, so houses being a good example of that. And it's generally simpler. In some cases, it can actually be a bit more complicated, but what's interesting about it is that it gives you much, much lower loads typically. Not necessarily that much lower, but they're typically lower than the directional procedure. So again, you can get some savings there on say your shear walls, on your sheeting or something like that. And you still obviously conform it to the code. So as we discussed, this is the loads that you would use, say, if you're designing your diaphragm or your shear walls. if you had, say, moment frames that you're using to resist your wind loads, you'd be thinking about the main wind force resisting system loads. This is also what you'd be thinking about for your foundations if you're thinking about overturning or sliding forces or something like that. And one important distinction here, and we've heard that question before, so I wanted to make sure to speak about it here. Wind loads in ASCE 7 are calculated at the LRFD level. So the load resistance factor design. If you're working in ASD, which is typically what we'll be doing in residential design, these loads are multiplied by 0.6. What's really important here when you're working, say, in ClearCalcs, and I believe most other software, you will actually enter the wind loads at the LRFD level. And the reason for that is that nowadays, the IBC ASCE 7, they include that 0.6 factor directly in the load combination. So I just took this picture from ASCE 7. And you can see that, say, load combination 5, you've got dead plus 0.6 times the wind. So that 0.6 is to convert from the LRFD loads to the ASD level. So that's where that comes from. So want to be very careful about that. Obviously, if you're multiplying by 0.6 your loads before you put them in ClearCalcs, they're going to get multiplied by 0.6 again. So you'll be drastically underestimating your wind load. So definitely something that you want to be mindful of. Okay, so now we are going to look at a design example in ClearCalcs. So we're going to focus a lot more, obviously, on calculating the wind loads, but figured it's nice to see it in application. And so what we're going to be doing is design a stud wall spanning 2 floors. I put an example picture here. And we'll be designing this in Lincoln, Nebraska. It's a gable roof, and we've got different design parameters here. And so I'm going to switch into ClearCalcs now, and we're going to look at designing this. And what I'll do actually is I'll do this. If I go to ClearCalcs, can you see my ClearCalcs?
Yep, we gotcha.
Awesome, great. So I'm just gonna say wind webinar and project address. I apologize, I should have copied it. If I go back to the presentation, here we'll see it's 920 O Street in Lincoln, Nebraska, near City Hall. So I can come back here, 920 O Street, Lincoln, Nebraska. And I can see here I'm in Lincoln, and I've got my little satellite picture. And already I'm looking at this, and I can start thinking about, ooh, what exposure category is this going to be? This looks pretty urban. So I'm going to create now a new calculation, and I'm going to scroll down into the wind loads calculator. And let's start with the components and cladding. We discussed about if we're doing a stud wall, we're looking at the individual stud as a component. We want to make sure it's strong enough. So we'll typically be dealing with components and cladding loads. So I'm going to create this calculation here. And first thing I see, type of calculation, components and cladding. So we're good. First question, basic wind speed. So this is something that we're working on soon. Ideally, we'll be able to just calculate this for you. You'll just put in your address. We'll put it there. But it's not quite something we've got right now. So in the meantime, what we recommend is this ASCE 7 hazard tool. And you can visit it at asce7hazardtool.online. And it's basically got a map of the United States with different wind speeds. This is basically the same map that's in ASCE 7, except in a digital format. So I already entered this, but if we go back, say we want to enter it again, Lincoln, Nebraska, I'm going to pick ASCE 716. See, there's also the 2010 and 2022 editions, but we'll keep it to 16. Risk category. This is typically for a residential building, risk category 2, where 1 would be for very low occupancy buildings, and 3 and 4 for higher importance buildings. And that's this. We don't need to select the soil class because that's for seismic. We're only going to look at wind loads for now. So I'm going to do view results. And I can see my wind speed here, 111 miles per hour. That's my speed. And if I look here, I can see I've got the different wind speeds, but the only one I care about right now is 111. So I'm going to come back to my calculation and I'm going to put 100 miles per hour. Exposure category. I mentioned it earlier, but we can go back to the project details. Oops. And actually, why don't we go back to the presentation? We can look at it very briefly. If we're in the middle of Lincoln, Nebraska, we're definitely not by the water like this. We're not in the middle of a field. Therefore, we're almost certainly in exposure B. And if we think about the entire lifetime of a building or a house, it's pretty reasonable to expect that it would stay in exposure B over its entire design life. So I'm going to go back to ClearCalcs now, and I'm going to change this exposure category to B, urban wooded areas with many obstructions. And already you can see the table here with the wind pressures just went down, but we'll get back to that. Okay, next we're going to need our building properties. So we know it's a gable roof. And if I come back to the example, right here, I know my plan dimensions are 40 feet by 30 feet, and the ridge runs along the long dimension. So I'm going to put this. So perpendicular to the ridge is 30 feet, and my length is 40 feet. And that's perpendicular to the ridge or parallel to the ridge. I'm going to enter my rooftop height, in this case, at 25 feet. Let me just open this up again. I can see here it's 25 feet. And top plate height is 20 feet. And this is my bad. When I wrote this, I should have mentioned rather the roof pitch. It's going to be 4 and 12. So if I look here, my roof eave height now is at 20 feet. And my roof pitch is at 4 and 12. And lastly, for my enclosure type, this is what we talked about. Enclosed is better in terms of lowering your wind loads. Partially enclosed is conservative. And for most residential buildings, when you've got windows, you've got doors, you've got patio doors, garage doors, you're almost certainly going to want to keep this as partially enclosed. And I can see here in terms of terrain properties, because I entered the address for Lincoln, it's automatically determined my ground elevation at 1,180 feet. If I wanted to, I could set this to no, and I could just set this to 0 feet and call it a day. And then this is always conservative to use 0 feet. In this case, I'll leave it at the auto determine, and we'll do this. Once that's done, we can see here we've got our internal pressure coefficient, 0.55. So that relates to our enclosure type here. So if I made this enclosed, you could see it's 0.18. So from 0.18 to 0.55, that's a big increase in wind pressures. And you can see here, that's all this is. And next we can see the different coefficients. We really don't need to linger on this, but this basically just takes the values from the ASCE 7 tables and puts them into ClearCalcs. Where things get really interesting is looking at this table here. So I mentioned when we're talking about components and cladding loads, that these vary based on tributary area. And so you'll see that there's quite a few lines here. The top part here, you can see there's the 0. So positive pressures are cases where the wind is pushing the building. So it's pushing into the wall, and you can see these pressures are typically lower. At the highest is on the walls, where we've got 25.7 pounds per square foot. And then we can see that as the wall area increases, this goes down all the way down to 20.7 pounds per square foot. So a good chunk less. Similarly, we've got on the negative side, that's when there's suction. So the wind is pulling the wall, is pulling the rafters, is trying to do uplift on the roof. That's those negative wind pressures. And obviously these get a lot lower. And again, these vary based on the area. So the two horizontal red lines here, they're the minimum pressures by the code. So we're going to ignore those. But if we look at, say, zone, I'm going to zoom in a little bit, 3R, which is the corner right at the ridge, at the top of the ridge, at the edge of the gable end. I can come here, and if I look, it's the dark green area. So if I look 3R, up until 10 square feet of wind area, I'm at almost minus 70 pounds per square foot of uplift. And then as soon as I hit 100 square foot, I'm at minus 39. So almost doubles the load area when we're looking at small components. So Again, this 70 pounds per square foot is something that a shingle might feel, whereas the 39 pounds per square foot, we're at 100 square foot wind area, that might be like what the ridge beam would feel. So once we've got this, obviously it's not quite practical to just read it off the table. So we've got this tabulated here, these wind pressures, and these depend on the wind areas that we enter here. So we'll leave the roof because we're only looking at stud walls right now. So for a stud wall, we talked about a 20-foot tall stud wall, and we'll assume we're at 16-inch spacing. So I can just type in 16-inch times 20 feet, and I can see my wind area is 26.7 square feet. So if I go to my table here, I've got all these different values you can see. So zones 1, 2, 3, if I look on the diagram, are all on the roof, and zones 4 and 5 are on the walls. Since we're designing stud walls, we're only going to look at zones 4 and 5. And this is where I look. So 24.4 pounds per square foot, positive wind pressure. So the wind is pushing with 24.4 pounds per square foot on the wall. And negative wind pressure, I can see zone 4 minus 26.1. So the suction's a little higher than the positive pressure. And then zone 5 is even higher at almost 30 pounds per square foot. So if I go back to my diagram, I can see zone 5 is in the corners. So it makes sense that we'd expect slightly higher wind loads here. And I can see that these corner zones are defined by this A variable. If I scroll down, I can see it here. Corner zone width, 3 feet. So I know that if I've got 16-inch spacing, I'm going to have at least one stud that's basically taken up a full wind pressure on zone 5. And so conservatively, I'm just going to take this minus 29.8 PSF. That's basically all of this to get that minus 29.8 PSF value on my stud wall. So now let's just quickly look at how I might put that into a calculation on ClearCalcs. So I'm going to create a new calculation. And I'm going to create a wood column. And we'll do the ASD wood column. And I'm going to go to the right and do a exterior stud wall. Okay, we'll let this load, and I'm going to close this. So right now I've got a 2x6 number 2 Douglas fir. That's fine. So first thing that will change is the column height, or the stud wall height, and we'll put in 20 feet. And already we can see it's failing now because of the deflection, but that's fine. And everything else will stay the same. It's not braced in the strong axis for buckling, but for weak axis, the sheathing presumably braces it against buckling. Our supports, it's supported at the top. That's where it lays on, and then at the bottom, that's where it lays on the ground. And at the top, we've got just a 20-foot roller, which means it's resisting the lateral loads. They might be going into a diaphragm or a wind beam, but obviously it's not taking vertical loads since those are all going to the ground. So I'm going to keep scrolling now. And I can see I've got my 16-inch spacing on my my studs. That's what we use in our wind calculation as well. Then we ask for the default load eccentricity. So by default, we'll put in 1/6 of the depth of the stud. And the reason we do that is literally just so that we can be conservative, because we don't know if the load's going to fall right in the middle of the stud. So it's a kind of a conservative assumption. We don't have to put this in. The code doesn't necessarily require it, but it's generally good practice. So we're going to leave this as is. Now, this is where we could enter the distributed gravity loads. So for instance, a floor load, this is our default values. We've got 8-foot tributary width and then 10, 40 dead live loads. We're going to delete this for now, because if I look at my example here, I can see I've got 100 pounds per linear foot dead load and a 200 pounds per linear foot snow load. So I'm going to come back here and just enter these as loads. So I'm going to enter this as roof load. I can see my eccentricity is the same. This one's in feet and this one's in inches, but it's the same value if you look. 0.917 is 0.0764 feet. So that is entered by default. I could make this to 0 if I wanted to, but no need right now. And I'm going to enter my loads now. So I said dead load 100 pounds per linear foot, and snow load, 200 pounds per linear foot. Just want to make sure that's what it was. Yeah, 100 and 200. Okay, and so I'm going to close this. And the last thing to do, obviously, is to add our wind loads. So you can see by default, we've got these wind loads. You can see the spacing, it just matches. It's 1 foot plus 4 inches, so 16 inches. And I'm going to open this load magnitude. And right now you'll see we've got wind down or lateral and wind up loads. What I'll typically recommend, unless you're doing something a bit more advanced, you can, for walls where you're looking at lateral loads specifically, you can generally remove this wind up parameter. Or if you want to be safe, what you can do is you can enter both values with a negative sign on the wind up thing. What it does, the wind up, is it gets used with 0.6 times the dead load times your 0.6 times the wind load, whereas the wind down and lateral gets used with the full dead load. So if I just go back quickly to my wind load, let's just make sure we're using the right number. I'm going to scroll down. Again, we're looking at zone 5 on the corner here. If I scroll down, I can see my worst case, zones 4 and 5, is 29.8 pounds per square foot. So I'm going to go back now to my column. And I'm going to enter 29.8. And if you see this project default thing, by the way, this might be a case where you could enter your own wind loads directly in the project defaults, and it would just use those by default when you create these stud calculations. We're not going to use those right now. We've run a webinar before on using project defaults, and I encourage you to take a look deeply into it. What I'll say is these project defaults, we're actually looking at ways to make them a bit better. So if you've got any suggestions, or if you want to share how you're typically using our project defaults, or if you're not using them, or if you tried using them, we'd love to hear your thoughts here. But anyways, all that to say, I'm going to put in my 29.8 pounds per square foot. And on the upwind, I'm going to also enter minus 29.8. Again, this one is typically where you would enter your lateral loads, the wind down or lateral. The wind up, we just enter it to be safe, but you don't necessarily need to add it, but we'll add it in this case. And with that, if I look here, I've got my design conditions, repeating member, dry conditions, temperature less than 100, which makes sense for Nebraska. It's not incised, etc. So we're good here. All that we have to look at now is, let's look at what's governing. So right now, what's controlling our design is the deflection. We can see in terms of interaction, we're good. We're at 96% utilization, but our deflection, likely from the wind, is getting us in trouble. So we can open our member selector, and let's stick with Douglas fir. So I'm going to type in Douglas fir in the filter here. And what I can do, say if I wanted to use number 1 grade, I can go and I can see 2x3, 2x4, 2x6, 2x6 passes for everything except for governing limit. In this case, we know that's deflection, but a 2x8 seems to pass for everything. So if I select a 2x8, I can now come here and I can see everything passes. I can see it is my governing, being governed by the deflection. In this case, it's 0.742 inches over 20 feet. So we pass with our 1 inch deflection limit in this case. So with that, we've designed our exterior stud wall to resist the components and cladding loads. So again, we started by creating a components and cladding. We went to the ASCE7 tool to find the wind speed to use. We looked at the exposure category based on just the Google Earth view or knowledge of the area, knowing that this is a urban area, therefore it's going to be shielded from the wind. We calculated our effective wall member area based on the span of the tall wall studs and their spacing. So we're good here. We entered obviously our roof geometry. We looked at the ground elevation factor. And obviously being in Nebraska, Beautiful state, but not a whole lot of hills present, so we didn't have to consider that in this case. So that's basically it for our first example. I'm just thinking now, maybe before we jump into the second one, if you have any questions about this one, now might be a good time so we can just go over it right now.
Yeah, thanks, Laurent. We had a few questions come in from Andrew. The first one, so this example, we had a gable roof, but he mentioned if we instead had a building with a flat roof and a parapet, is there a way to get the parapet components in cladding in ClearCalcs currently?
Great question, Andrew, and thank you for bringing it up. That's actually on our to-do list. We don't currently support parapets, and then the reason is because we were mostly focused on small residential buildings where you wouldn't necessarily have a parapet.
Jesus fucking Christ.
Excuse me?
All right.
Oh.
There's a reminder, probably want to keep yourself muted. But anyways, thanks for that. Right. Yeah, a little sound bit there. Okay, so yes, Andrew, great question there. Like Laurent mentioned, so in the past, we were 100% focused on the residential, which is why we didn't have it. But now the engineering team is focusing not only on residential, but also on commercial and light commercial. So that will be something that'll be coming. And then next, so Andrew had another question here. So when you were going from the components and cladding into your column calculator, there was, if you can go back and like scroll a bit down into the outputs in your wind, in zone 5, the positive wind pressure is 24.4, the negative wind pressure is 29.8. So if you put the positive 24.4, does that mean the negative 29 is not used in the snow and dead load combination, or are both checked and then the worst case used?
Okay. So this is where it gets a little bit tricky. What I would suggest is we just take a look at the load combinations themselves. And I think that might hopefully enlighten us a little bit. If I open the load combinations here, we can see, so this is in the load combinations section. I can see I've got here a load combination. This is to match the code, but it's basically dead load plus 0.6 times wind down or lateral. If I look then at my wind up, I've got the 0.6 dead plus 0.6 wind up. And so what that means basically is whatever wind value you enter in the wind up category will get combined with the 0.6 dead, and anything you enter in the 0.6 wind down or the wind down category will get combined with the full dead load. And then when we're talking about combined with the live load, the snow load, etc., that's also going to be the wind down that gets considered. I hope that clears things up, Andrew. I'll be completely honest, this might be a little one of our more confusing aspects, and it's something that we're looking to make less confusing. So if there's a way we can make this make more sense, we'd love to hear it, and we'll see what we can do for the team.
Yeah, and let us know, Andrew, if that answers your question. I'll go ahead. I just clicked to unmute you if you want to expand on it a little more. Want to make sure we're getting that question answered because it is a good one. And then, oh, looks like you were unmuted, Andrew. Any further comment on that? Maybe your mic doesn't work. All good. If for some reason you do have further questions, send it in the chat and I'll make sure to bring it up. As of now, that's all the questions, Laurent. So yeah, we could either move on to the next one or yeah, just continue along.
Sounds good. So let's keep going. And so our second example, basically, we're going to keep it simple with the main wind force resisting system loads. We are going to basically look at the same building, except we're going to look at main wind force loads this time. And so I'll jump straight into ClearCalcs. And what I'm going to do now is I'm going to go back to this wind calculator and I'm going to create a copy of it So if I come here, this button right here, duplicate. And you can see all the same parameters are being used. Everything is good. What I'll do just to remember it is I'll do main wind force resisting system. And that way I remember that this is it. And if I look at my type of calculation, I just have to switch now to main wind force resisting system. As you can see, all my parameters are still here. Everything is still the same. The only difference is obviously these coefficients have changed and these values on the right have changed as well. So this is basically all we need to do right now to get the loads in PSF. And what we'll be doing now is we look at, we've got wind pressures for the case where we've got positive internal pressure. So that's when the wind is blowing air into the building and it's filling up with air like a balloon, and negative internal pressure, which is literally the opposite, where you've got wind being sucked out of the building and it's kind of being imploding on itself. And so what we can do now, obviously, we've got our loads in PSF. The natural question is, well, now that I've got my loads in PSF, how do I convert those into loads on my shear walls? And what we'll do is basically we've got these diagrams to help us. And so if we wanted to look at, we've got two load cases, right? Load case A, which is typically going to be the wind loads being applied perpendicular to the ridge. And then we've got load case B, where we've got our loads being applied parallel to the ridge. If I wanted to say, look at load case A, what I would do is I could look at all these different zones and I could just sum up their loads. And so in this case, this is actually a feature that we're working on right now. And literally as I speak, we've got someone on our team programming this to be automated. But what I would do is I would take, say, I would look at the positive internal pressure and the negative internal pressure, and I could literally just sum up these values, and I would take their, say, horizontal components, especially for the roof, multiply them by their tributary width. So say if I'm looking at zone 4, for instance, where I've got 16 pounds per square foot wind pressure being applied, I could multiply that by my zone 4. I know that my walls are 20 feet high and presumably half the load is going to the ground. So I would multiply this minus 16 PSF times 10 feet tributary width, and I would get 160 pounds per linear foot being applied to my building. Now I'd also want to look at my edge zone here, which basically accounts for the corner effects and a little bit of turbulence happening there. So I see I've got 19.4. Again, I would multiply that by my 10 feet. So I'd get 194. This is going to get a little hard to track. So I'm gonna stop here. But I think you can get the idea here where we multiply these values in PSF. At the same time, we do the same thing for zone 1, zone 1E. And then we just take the sum of these. So you can see we've got some negative symbols, some positive symbols. The idea here is that these all add up together. Some areas might have some suction. Some of them might have some positive pressure pushing on the walls. That's what we're looking at here. And then I would do the same thing for the case where I've got negative pressure into the building. And from that, I could get my loads in pounds per linear foot being applied to the building. And with those ones, I could then multiply them by the tributary width for my shear walls and put those loads into my shear walls. So this is something that we're working on. The idea here is that basically you'll be able to just create a shear wall calculator, or it'll probably be something like a diaphragm calculator. You'll be able to just directly link these wind loads. We'll run the math for you, and then you'll just get your values that you can then link into a shear wall calculator. Let us know in the chat if that's something that interests you, if that's something that you would see yourself using in your workflow, or if that's something that you could see a different way to do it. We're working on it right now, so now's your chance to kind of have a big impact on what it's going to look like. Otherwise, I think I'm going to stop here. I'm going to go back to our presentation quickly and just conclude. Basically, obviously, wind loads, very important thing to think about when you're designing buildings, including residential buildings. The most important thing to think about is the wind speed. And we spoke, especially if you're near the coast, you want to make sure that you're using the wind speed specifically for where you are. But there's also other things to consider. probably the most impactful one is topography. If you're in an area with a lot of hills or you're building on top of a hill or something like that, there's two types of wind loads that we apply: components and cladding, and the main wind force resisting system. Components and cladding, obviously, for really local aspects, as big as a rafter usually. Then the main wind force system, which is when you're thinking about shear walls, foundations, things like that. And ClearCalcs is here to help you. We run calculations for both of these in ClearCalcs, and we're always looking at ways to make them better for you, to make them more automated, to save you time. And we'd love to hear more about what we can do to help you, especially with the wind loads. Other things that are new at ClearCalcs, we just released, you're now able to enter, this is something that we've heard from quite a few of you, custom wood properties. So if you're dealing with, say, very old wood that's got different design values, or some fancy European species or something, I'm making this stuff up, but if you're dealing with this, you can just enter these values now, and we'll still run the calculations per the NDS, so you'll still be up to code. We've also got, we ran a webinar on this last month, wood and steel truss design, fully supported in ClearCalcs. Love to hear how that's going. And a recent one that we came out with as well is shear keys in retaining walls. So if you're looking to improve your sliding resistance. And we've got a couple webinars coming up. Very excited. We've got one in 2 weeks with Ted Goldstein at Atlas Tubes, and he invented the Shuriken connection system. So you can see a little picture of it here, a little video of it here, but they're basically a system to connect HSS tubes without having to weld them or to drill them on site. It's a very cool system. We're really excited to have Ted on come on and tell us more about his invention and how to design with it. So encourage you all to be here. We'll also have a steel base plate design webinar on June 28th. And if you were here last week, we had a nice chat with David Ortekin, who is a mass timber design expert. And he's recently published a book on starting your own engineering practice. And he's going to be coming on with ClearCalcs to talk a bit about his book, and especially to share the wealth of knowledge, advice, lessons learned that he's experienced over his career. So to help you start your own engineering practice, or even if you're working in an engineering company and you want to understand a bit more about the business side, this is a really good opportunity for that. And that's it. Be happy to answer any questions if we've got any more.
Yeah, no more questions have come through in the chat. Guys, feel free to send through any questions you have. So Andrew asked, so he said, what about overhang loads? So what about how might you do that in ClearCalcs? I'm just looking at the clock. We have about a couple minutes left. So if for some reason we don't have time, we could always send Andrew a follow-up Loom video.
Absolutely. Thank you, Andrew, for the question. Overhang loads are another one that we're missing right now. If I go back to ClearCalcs, we can look here. So we're really looking at the most simplest of buildings. However, obviously overhang loads might be significant, especially if you've got large overhangs. If this is loads that you find are typically governing for your designs that you need to check, reach out to us. I'd love to see like an example or something like that, because that's definitely something we can add into ClearCalcs.
Perfect. So those overhangs and then the parapets are the two that we got to get added in there.
That's right. That's right. Andrew, you nailed us on both.
Love it, though. That's why we have these webinars. Well, not the only reason, but part of the reason, so that way we can get that direct feedback.
Exactly. Thank you.
Yeah. Also want to note, so Laurent kind of really quickly ran through a how-to example in the last like 5 minutes there, but I know a question I get a lot is, how do I take the PSF, the pounds per square foot loads from these calculators and implement it into, say, my shear wall calculator as a pound load? Like Laurent mentioned, that's something that we'll be able to automate here pretty soon in ClearCalcs. If that's something that you either struggle with, I guess I never ended the poll, so I'll end the poll now. But transferring wind loads to my buildings was 60% the most annoying part of calculating wind loads. So reach out to us at help@clearcalcs.com, because that is something where we're going to want as much feedback as we can get when we implement that new feature.
Absolutely. Absolutely.
All right. And we're at about time. If you guys have questions that you didn't get to type in the chat, reach out to us at help@clearcalcs.com. And again, apologies for anybody who had issues on joining today. We'll make sure we don't have those same issues moving forward. And enjoy the rest of your day, everybody.
Thank you, everyone. I hope you enjoyed this and look forward to hearing from you.